Let's check whether the bulb is working. It's working. So let's check it in the ORS solution. Okay. Is it visible to all of you? Can you see this?
Yes.
No. Now they were touching each other, but without them touching.
Good afternoon, students.
Good afternoon.
Today we're going to discuss a very important topic in chemistry, which is about chemical bonding. There are several types of bonds, one of them being covalent. The word covalent indicates that the electrons are shared by the atoms connected through this bond. Of course, the bond could be equally controlled by the nuclei, or it may not be uniform, but it doesn't matter. We still call it covalent. And covalent bonds are found in molecules. There are substances that do not have covalent bonds between the atoms that make them. For instance, salts. A good example is sodium chloride. Sodium is an ion, so it's chloride, but they have opposite charges. It is the electrostatic interaction between them that keeps them together until something like a solvent, in this case water, pulls them apart. Today's demonstration will help us see if the bonds are either covalent or ionic. If the bonds are ionic, there are freely moving charged particles that would complete the circuit, which otherwise would not conduct current. So from here on, you try to explore what kind of bond you have in the following solutions. Ready? You could start. Thank you.
To demonstrate today's experiment, we'll be using this apparatus. It is simply just a couple of battery dry cells connected by a copper wire to a bulb. So we'll be checking whether the compounds we have in front of us are covalently bonded or ionically bonded by the fact that they light the bulb, because they will have free ions within them. Now, to check that the apparatus is working, we'll connect the two wires together. As you can see, the bulb will light. So when the two ends of the wire connect to each other, the bulb will light. Now we'll see in which compound will the bulb again light. So let's introduce the compounds we have. We have here pure water. Then we have sodium chloride or normal table salt, which is in solution form. We have sucrose, which is table sugar in solution form. Then we have lemonade, squeezed from a fresh lemon. And here we have a common drug which we use for young children when they get sick, which is lem, commonly known as lem or ORS, oral rehydration salts. So we'll insert the apparatus into each compound and we'll see whether they are covalently bonded or ionically bonded. So before we insert, we have to rinse it just to clean it. This is the water we'll be using to clean our apparatus. So let's insert to the water and let's see if the bulb lights. Are you seeing any light coming from the bulb?
No.
Okay. So that means that water is not an ionic bonded compound. It's actually a molecule. That means it's made by covalent bond. So I'll raise it again, the apparatus. Then now I'll insert into my sodium chloride solution. Okay. Okay, are you seeing lights coming? Let's make it very clear. Let's switch the apparatus so that we can completely immerse the wires in the solution. Are you seeing a little light coming from the bulb? Yes. It might be small, but it's still coming. It's maybe dim because of the concentration. We have only taken a small amount of the solution. That's why maybe it's dim. But it still has, the bulb has still light, so that means that sodium chloride is an ionic compound. So we'll rinse it again. And we'll insert it to the next compound, which is sucrose solution or table sugar solution. So what would you expect to come from this? Look at what would you expect to happen. Okay, let's see. Okay. Are you seeing any light coming from this?
No.
So what does this prove, Efrata? What can you understand
I
from
think
this?
it's because sucrose is a molecule. It's an organic molecule, so it's made from a covalent bond. That's why we don't have that.
Yes. So we have proved that up to now we have seen that water is covalently bonded, sodium chloride is ionically bonded, sugar is covalently bonded. Then we'll go on to the next, which is lemonade. First, we'll rinse our apparatus. Let's see what happens in the lemonade. Okay. Is the bulb lighting?
No.
Okay. So, Kebron, why do you think this is?
I think it's because the lemonade is just citric acid, which is an organic compound, not an inorganic compound,
Yes.
and it's covalently bonded.
Yes. So, as she said, we have squeezed the lemonade. So it comes from a lemon, which is citric acid, which is an organic compound. That means it's a non-electrolyte, meaning it's covalently bonded.
Could you check if the bulb is working properly by connecting the
Okay.
wires
Okay. Let's remove it
by
first.
themselves?
Okay. Yes. When we connect it, the bulb works.
Still function.
So the fact that the bulb hasn't lit so far is from the nature of the compounds themselves. Okay, so for the last time, we'll check in our lambda or in our ORS. Okay. Is it lighting?
No.
Okay. But would we expect it to light in this ORS?
Yes.
Yes. Why would we expect it to light?
It's ionically bonded.
How could you know that it was ionically bonded?
I saw the ingredients.
Yeah, it says that it contains salts. So we have seen here that sodium chloride is an ionically bonded compound. So it was supposed to be an electrolyte. Maybe it comes from the concentration. So let's concentrate it a bit more. And let's see if that makes a difference. Good job. Okay. They're touching each other. I'll need a spoon to do this. Could you pass me a spoon, please? Thank you. Let's concentrate it a bit more so that you will see the effects. Okay, so let's see. Let's check whether the bulb is working. it's working. So let's check it in the ORS solution. Okay. Is it visible to all of you? Can you see this?
Yes.
No. Now they were touching each other, but without them touching. Okay. We're not seeing that much of a light. Yeah, slightly. But we had expected that lambda would be an electrolyte. So what do you think went wrong here? Can you give us a shot?
The number we added in the solution. I mean the concentration.
Okay, so the concentration has an effect because we need much ions. No, the fact that it lit now is just because it touched each other. It's not because of the compound. So
It's slightly visible.
yeah, slightly visible. Just a small amount. It's not that much though. Yes. So we have seen a dim, very, very dim light. That means it's earlier we didn't see any light. So now that we saw a very dim light means if we keep on adding the concentration of the aluminum, we'll have a more brighter light. So we can generalize that aluminum is an electrolyte, meaning that the constituents that it has are ionically potent. Yes. So
I have a question. Lemlem is supposed to be consumed by people who have lost large amount of fluid from their body, either through diarrhea or vomiting. And we're saying salt would replace the electrolytes so that the people will become normal once again. But there are people who should be careful about consuming salts. What kind of people are advised not to take salts? Ephrata? Not really.
People with high blood pressure.
High blood pressure, hypertensive people. If you eat food rich in salt, what do you feel? Thirsty. Your body is telling you to dilute the blood salt concentration. Otherwise, the body would react on its own. How would it react?
Do you want to drink more water?
From where? It would. The blood salt concentration is high, so the cells surrounding the blood vessels would be taxed. So they would be forced to give water to dilute it. If you don't drink lots of water, that would happen. And your cells would shrink because they have lost water. And the cellular chemistry is aquatic chemistry. If there is not enough water in the cells, they're going to die. And when more and more cells die, eventually the person dies. So that this does not happen, people have to be careful. But if somebody has lost electrolytes through dehydration as a result of many things, you could stand up in a heat outside in the summer, you could be dehydrated as well. So the amount of salt they add is judicious. They have to make sure that it does not go beyond the permissible level. Otherwise, the person could be also affected. So that amount of salt in it would not be enough to give us bright enough light to see for us. Would that explain it?
yes.
Okay. So, can you conclude from bonding point of view?
Yes.
Covalent bond. Would you like to be my co-pilot, Liu? I'm going to fly the plane. What will you do as my co-pilot? You will assist me. You will cooperate with me. The prefix co means to do something together. So covalency means the electrons are controlled by the two nuclei attached by them. In the case of ionic bonding, they don't share the electrons. One simply loses the electron completely, the other one gains it. As a result, a positive and negative ion are formed. Simple electrostatic attraction keeps them together. The moment you put them in water, they dissociate. They become free. Now, if you don't mind, I'm going to give you salt. Because salt conducts electricity as we saw it. Okay? Here. Dip the electrodes into it. Now, hold it for her. See how bright the light will be now. Dip it. Immerse. Wow, what happened?
There's not.
Why not? This is sodium chloride.
Because it's not dissolved. Or it's not in its aqueous solution.
Well, we have sodium ions here. We have chloride ions here, as we do in the solution. But we don't see current.
Because here we have mobile ions. They're free. They have to move around. So they'll create a networking bridge between the two wires. But here they're not mobile. They're in a compound form, in crystal form.
So it is not enough to have ions to see current. You must have ions, but the ions have to be mobile. So they have to be free. How did we make them free?
By dissolving them.
Does water dissolve salt?
It's
In aqueous solution.
solution.
It should be an aqueous solution. It means ionic compounds conduct electricity if the substance is an aqueous solution, so we should pour solution.
Like dissolves like. Water is polar. Are these polar? The ions? Definitely, extremely polar. Ionic substances are extremely polar. Therefore, they readily dissolve in water and they become free. What do you do if you don't have water to free the ions? What else? What other method?
We can melt them.
Melting. So molten sodium chloride is also electrolyte, because the ions are once again free and mobile. So these are things that you need to keep in mind. And would Ephrata say something about this? Why did I bring lemlem here?
Because,
What am I trying to show?
because as we stated here, it's formed from different types of salts. So that means the salts are ionic compound. So this is an electrolyte, or we can make them light.
If you have somebody completely dehydrated, far away from a major city where you could get lemlem, how would you help that person? There is no lemlem there, but the person is at the 11th hour knocking at the death's gate. You don't want him to die. What do you do? How would you help this person?
We'd advise them to mix salt with water and drink it. As
Exactly.
substitute.
What if you don't have distilled water or clean water? Would you not give that person that salt solution?
No. They can filter it by traditional means.
Even if you don't have a filter, what do you do? But there is no fire. Well, I would give it right away. It's better to have, say, amoeba or giardia, which would be treated later on, once the person survives. This is very critical. In fact, I call this the best medicine on earth, because it's very affordable. How much did I pay? 4 birr and some cents. And it saves life. And which age of the population benefits from this?
Younger.
Yeah, babies usually, because they're not careful about anything, so they consume something and they have some problem. They end up with diarrhea, vomiting, lose large amount of water. If you don't help them with ORS, they can die. But this is a very essential drug. Don't waste your time and energy to save people who are over 80. Once I get to 80, I'll change my mind. So, thank you very much. We're done with this.